So I'm pleased to introduce Taylor Asher. He has degrees in engineering, Spanish, and marine science with a focus on mechanistic and statistical processes in coastal flooding. He's worked for private, public, and academic sectors on a range of issues in coastal water levels, waves, and flooding. He's currently a researcher working under NOAA to develop new ideas and methods for predicting coastal water levels over subseasonal to interannual timescales via both observational and model data. He's also engaged in several other studies, including artificial intelligence-based tsunami prediction, stochastics in tropical cyclone meteorology with climate change, data assimilation methods for water level climatologies, and uncertainty quantification in coastal water levels across timescales. And I really like your title, Stuff on Winds, Water Levels, Uncertainty, and Us. So with that, I'll turn it over to you.
Thanks. Am I audible online now? Awesome. All right, I'll start over. Yeah, so I had a much more specific and sciencey title and kind of set of material to talk about when I first put out my abstract before I got here. And then since I've been meeting with everyone this week and so many different things have come up, I decided to go much less focused on a single set of work and much broader across different things that seemed like it would probably be relevant and interesting and whatnots to everyone here. So yeah, a title became the very last thing I thought of doing when I was putting these slides together, and oh, that's what I got. But yeah, so here's coastal flooding broken down by the mechanisms that we mostly think about. The baseline is kind of the sea level, which really incorporates a whole bunch of baroclinic processes and different things, and of course things like sea level rise and stuff. I just put it in one layer because it's too many otherwise. I also threw tides in there because why not? Then on top of that, we get storm surge is kind of the longer wave, if you want to think about it, coming in. And then regular waves, like surfing waves on top of that, which they also break and that creates what are called radiation stress gradients in the water level that create their own sort of water level setup on top of that. And then when you get really right up to the coast, then the waves actually break and perform wave run-up, which in some areas is actually the dominant hazard in certain steep coasts. So it's a whole bunch of different pieces and what matters changes, and then you get into barrier islands and back bays, and it's a whole thing. But the reality of it is stuff like this. So wait, no, go this way, okay. Stuff like this. This is an aerial picture after Hurricane Sandy in 2012 in New Jersey. And not only are you getting all these physical processes, but also there's all this built environment that starts getting thrown around at other pieces and creating its own destruction, and sediment starts moving, and it's a messy thing. But the first completely random topic that I thought I might throw in here is what is called Ekman waves and Ekman setup. And this is a simulation of Hurricane Michael. And you can see the arrows are the winds, the colors are the water levels. And as they're going up and down as the storm comes along here, that's all tides happening a couple times a day. But then as the storm starts to formulate here, the video restart, the storm starts to formulate here, and you can see along this area, yeah, the tides are coming along and going up, but there starts to be this other persistent water level rise. And what this is Ekman-based setup where winds are blowing this way, but they're doing it over a longer time scale such that the Coriolis effect means that the water levels actually get deflected off to the right. And so you actually get a meter or more of water levels increasing. And because the storm is moving and the water levels are moving, these things can actually interact with each other in a quasi-resonant state that will create these long waves that propagate along. And then when you get a turn in the coastline like we do up in the armpit, the Big Bend of Florida, then you can get those collapsing all together. And so the largest surges in that storm were actually quite a ways away from the center. Hurricane Dennis is probably the best other example of this, and Hurricane Ike is probably the most famous one because it had over 3 meters of water level driven just by Ekman's setup. Now, across uncertainty, which is a lot of what I explore in this, there's this tricky part about it where when these estimates become tougher to predict, the bars get larger and larger, we have a tendency to want to throw out these data. And that's really easy to do, but the only reason why, or not the only, we probably would have figured out eventually, but the original reason why we know about these Ekman processes is back about 100 years ago, a scientist out on some cruises noticed that when the wind was blowing this way, icebergs were going that way, and thought quite reasonably, that's kind of strange. And so even though that's a very small, observation, it still persistently seemed to point to something. And it was because of that he came back and talked to this mathematician named Ekman that then went, full-blown mathematics on it and figured out the why, and now we're able to predict it and all that. So there's a lot of value in these things, even when the points are off and there's some questionability in the data and things like that. And I found this quote by Voltaire once that I find is probably the best way that I like to think about these sorts of things, is that you don't really want to think about these fuzzy gray areas and ignore something beyond what your model tells you, but in a lot of ways you don't have another choice. And that has other really severe and heavy-handed implications. This is a picture from Hurricane Gustav in New Orleans along the levees on the Mississippi River. And when you look at it from another angle, you can see that these water levels were literally inches away from overflowing this roughly 4-meter tall seawall. And that's a lot of good luck, but that's also a lot of uncertainty. At any point earlier on, the forecasting uncertainty and how that could have changed easily could have brought that water level over. Even if there wasn't forecasting uncertainty, the quality of the water level model predictions also could have been off. Even if those were perfect, the performance of the people that designed and built that wall could have been off, and it could have broken, and those poor news reporters could have had a much worse day. There's just, how high it was designed to be. It's, also just very lucky by chance that wall was designed to just the right height for this storm, for this moment. Yeah, there are uncertainties in a lot of places, in a lot of ways, this next section is kind of exploring on how we can try to deal with those, continuing in the forecasting space. The idea came out of a question someone asked me one time about, given the fact that we don't have enough time to actually run good models, what do you want to do? How should we run some models when we're forecasting things? And so I came up with a wish list of what we would be able to do. The first one was maybe a little self-evident. The next one also, but the third one I think is equally important. And I know a lot of people want to understand things looking at what might happen under different scenarios if the storm turns left or right or different things like that. And so the probabilistic information has a lot of value. It also can't tell you other things that you can learn and figure out by looking at things in a scenario-based way. So I thought, wow, I'd really like something where someone can say, okay, but what if this happens? And you could reasonably quickly get that answer without having to go back and run more numerical models and all that jazz. Also, just in terms of efficiency and things, it makes sense to try to be able to recycle some of the information that we've done from the previous forecast cycle, since these things come so often. And also that there's better specificity, that we'd be able to take advantage of things like the increase in numerical weather predictions and ensemble members, and pulling some more power there in terms of how the forecast cycles change and how some storms, their actual forecast uncertainty can and oftentimes is very different than what the climatological, so to speak, averages are. And then, just it's always nice if you can come up with a framework that isn't only going to be useful for a couple of years and then get thrown to the wayside. And so trying to think about something that might work with this and allow us to move forwards with better models, because that's another issue. Is for a long time, the only thing that's really been used for probabilistic water level forecasting is really low-grade numerical models, because they cost a lot to run, they take a lot of time. When you get away from the really long-term established ones, there are stability issues and things like that. And so the approach that myself and some folks who specialize in stats and applied maths came up with is basically a approach using surrogate models. And the starting idea is hurricane season isn't year-round, so hey, if you have some compute cycles on the off-season, just run a couple of storms to give yourself just kind of a background population of data, because again, it's nice to optimize the usage of these compute cycles when you can. But that's an optional step that we only sort of leverage for our first study. And then once the first advisory comes in, the basic idea is to try to select and run a few number of storms. I don't know why this is auto-advancing. A few number of storms that best improve the storm surge forecast. And that's given a couple pieces of information. One, what storms have already been run, which we of course know. The storm forecast, which we're going to take the NHC as the best guess because it's certainly a good starting point. And then we're going to make some assumptions about the forecast error, in other words, going from a single forecast to a distribution of probable outcomes of the storm. And also the uncertainties in the surrogate model that we're going to be constructing, which is assumed, but you can construct based on data that we have and things like that. And so you run those simulations, you then reconstruct your surrogate model, and once you have that surrogate, it's relatively easy to take that assumed forecast distribution and integrate across it and come up with probabilistic flood hazards for your area of interest. And once you have those, then you can just sit around and wait for the next advisory to come out, because of course everyone always has lots of free time in forecasting. This was just a pie in the sky idea, and we wanted to do a proof of concept study. So we did that with Hurricane Michael in the Florida Panhandle. The storm was nice because it came up quickly, it caused a lot of damages, and it had some unusual characteristics about the tracking and things like that. We used a high resolution mesh with the AdCirc model of this region. And a parametric wind model called the generalized asymmetric Holland model. It's basically if you take the Holland type approach, but then use the different isotac information to actually interpolate and come up with a wind field that closer matches some of the asymmetry structures. And then generate and run these forecasts every cycle from the start through the end. Actually, for this, we did it every other cycle. We did every 12 hours, mostly because we didn't have any funding for this. It was just kind of in our free time, and whichever one of our friends would be willing to take a beer and offer in exchange for some supercomputing time. And then for the surrogate, we used GPs, Gaussian process models, for people who are familiar with those. In terms of the parameterization, these were the core parameters we used. The longitude, the maximum wind speed, also the central pressure deficit, but I don't have that on here. The forward speed, and then the radius of the 34 knot, the outermost isotac radius that we get. And for our quote-unquote background set of data points, this is what we did. This distribution that I'm showing here is going to be our first forecast distribution. So you can see that our background points are independent of that. We just kind of semi-randomly, semi-uniformly sampled the space. And then for our first round, our first forecast, this is what our next sampling looks like. And you can see that what it's trying to do is both sample from that distribution in the most effective way, while also acknowledging that we've already got some points that have been run. And this is a look at what some of the different tracks are that come out of that. The color is the intensity of the storm. The circles are the sizes of the different radii around it. And so you can see that they're all sampled pretty differently. Some are pretty weak, some are kind of strong, just what you'd expect. And then skipping, what we did for each additional round, because I don't want to have to make you guys watch through 300 slides. Going from darker to lighter here is going from the latest forecasts to the earliest. And so you can see each round, these things tighten up, and each round, the sample points also tighten up where they're covering, because that distribution uncertainty is shrinking, and because there are fewer and fewer places that haven't been sampled in this. So that's kind of the machinery of how this works and the logic behind it. And now here's a look at how the actual performance came out. These two plots are RMSE, mean square error, and mean absolute error for water level at basically wet overland nodes. So what we chose to do is try to come up with the best solution anywhere on land where there might be storm landfall, since Those are generally the areas we care about. And we looked at this for 2 scenarios. One in which we don't know basically where the storm is going to make landfall, right? So the actual forecast setting. And that's what the black curves are here. And you can see there is a steady and pretty considerable improvement in model performance over time. I should add, since I know you guys aren't all surge folks, typical errors for like a good surge model are probably like 20 to 30 centimeters RMSE. So this starts off not good, which is not surprising because the storm was several days out and we only ran 10 events. But even after a couple of cycles, it really quickly picks up to some really good performance. But with the green line, what we can see is that the majority of this uncertainty comes from the fact that we don't know what the forecast is going to be and how it's going to change. And that's not really surprising, but this was nice in that it helps us quantify that. And then for the last step, what we did, because we wanted some more empirical comparison of performance, since we know things seem to go pretty well, but Michael was unusual. The actual forecast track error was pretty small, which is great because forecast uncertainty is kind of one of the most difficult parts. So what we did is we took the P-surge forecasts and their probabilistic water level estimates and then compared those to ours. So in these, we're looking at the 50% exceedance to the 90% exceedance levels. They don't provide anything below 50%, which is why that's the range that we're covering here. P-surge is on the left in red. Our stuff, which we called E-surge because it just seemed like an easy name for an emulator that also sounds like P-surge, is on the right in blue. And one key thing here is between the 50 and 90th percentiles, you probably mostly want the true solution to be within your coverage. And for the most part, we do get that. Some of the cycles with the highest surges, they do underpredict in both cases. And that's not uncommon because the highest surge is kind of the worst case scenario. So it oftentimes will exceed the 90th percentile. But in general, our performance is pretty similar to P-surge. And actually, excluding the very last one where they definitely beat us out, we actually kind of have tighter confidence intervals and better matching to the observations in the earlier cycles. So it worked pretty well, but this is also just one storm with some pretty unusual error statistics and things. But the really nice thing about this approach is that it's very generalized. All the pieces can be swapped out. So we could do this with some of the P-surge mechanics. We could do it with a completely different meteorologic model. The only things that you really need is having some basic interoperability with some of these things, which was kind of nice about this work. Then the next thing I wanted to talk to you guys about, the thing I actually mentioned in my abstract, has been the focus of a lot of my work for the past 2 years, which has been a major effort by NOAA to do a big coastal water level reanalysis. And so the general idea with this is to come up with a good simulated record of hourly water levels all across US and US affiliated territory coastlines. And by high resolution, I mean, and coastline, I mean, very high resolution, on the order of a couple hundred meters, and actually at the coast and even over land. So this is not an open ocean model. The model does include the open ocean, but the goal is really to get good solutions at the coast, at the near shore, and over land. The simulations are 1979 through the present, so we've got 44 years, and then leverage these data for a lot of different use cases, like nuisance flooding, records of historical storms where we don't have gauge data, flood frequency information, so flood hazards basically, some work with different sorts of water level outlooks from sub-seasonal to annual predictions, and then to make all this stuff freely and as easily as at least as feasible, available to people online. And so the basics of how this works, like I mentioned, hourly water levels all along the coast, 1979 through present. And then this is the look at the mesh extent. So we cover the whole western North Atlantic, basically, and of course the Gulf of Mexico. This is bathymetry, so deep ocean is deep. The coastline's a coastline, but you see all this red. That's because the mesh goes overland. It goes up to about 10 meters above sea level which is higher than what Katrina reached. So in other words, the mesh is able to capture any coastal flooding event's full flooding extent. And in terms of mesh design, it's tricky and complex, but some of the key things is that with flooding stuff, what you really want to capture is flow pathways, like deep and narrow inlets, which is what some of these things are that we've made sure to resolve, and then flow barriers, which include barrier islands, which we be sure to make sure the mesh follows, elevated roadways, which it also follows, different things like that. And then the other core piece of this method is that it uses data assimilation to capture a lot of the physical processes that aren't in the model. And that's because I didn't mention this yet, and I'll talk about it a little more in a minute. But the general idea is that 2D barotropic coastal ocean models can do incredibly good job of capturing tides and storm surge so long as their inputs are reasonably accurate. We have a very good sense of what the moon and the sun do, so that getting the tide inputs accurate is not tough. And with high quality reanalyses of the atmosphere coming out, thanks to work that you guys and everyone else in the other part of the world does, we had a lot of good inputs on that end. But there's still a whole lot of other coastal ocean processes that, just like on my very first slide where I just lumped a whole bunch of stuff into one little block, well, also with these sorts of models, they tend to be treated as kind of like a secondary and input parameter because, I mean, it's very tough to get a model that can capture glacial melt's effect on sea levels at the same time as it can capture the coastal flooding from Hurricane Irma. And so to capture all those things that I don't want to have to deal with in any way with real physics or math, what we do is we correct for what we term unresolved drivers. And these include, for instance, the steric effect, the fact that the water column heats up and cools down on seasonal cycles, and that actually causes it to expand and contract. Major rainfall events, which can create a lot of water that will eventually condense into rivers, go down and run off, and then can produce higher water levels in estuaries, things like that. Changes in major ocean currents, so the Gulf Stream, for instance, when it slows down, that causes coastal water levels to rise along much of the East Coast, sometimes pretty substantially. And its dynamism is driven by a lot of different things, from actually hurricane wind fields to the way Rossby waves propagate across the Atlantic, and again, lots of stuff that we just don't have there doesn't exist a single model that can really do all these things at once. And then sea level rise, which, yeah, it's sea level rise, and then also, this is kind of an asterisk one, but because of the way the methods work, it can also do a bit of work with helping us do a better job when the meteorology is off and it produces incorrect water levels. Not an unresolved driver, I know, but it made sense to put it in the list here. So this is a piece from the paper in which we developed the methods for the assimilation, and the video here is a look at Hurricane Matthew in 2016. That white dot is it going along its track, and the colors represent the water level correction in meters, so it's 0 to 50 centimeters here that's being applied during the simulations we did for that study. And what you can see is, of course, it changes in space and in time. And in particular, so as the storm comes up, you start to see a bit of a development of a rise in sea level along much of the South Atlantic Bight. But then as the storm passes, this really starts to turn to huge levels. And what this was Hurricane Matthew, thanks to its track, which means the pressure was kind of right over the Gulf Stream and its winds were really pushing against it, managed to shut off about 30% of the Gulf Stream's transport, which is huge amount of water that it managed to bring to almost a stop. And that caused sea levels to really go up for many, many days after the storm. But yeah, so the basics of the method for this reanalysis is we run the coupled Adserk and Swan model for waves in circulation, and that's forced by tidal harmonics. Like I said, that's kind of what the sun and the moon do to us with tides. And then ERA5 meteorology, which in particular is surface winds and pressures. Once we run a simulation for that, we're doing the simulations in 1 year increments, but you can think of it as being for the full 44 years. Then we compare to NOAA water level gauges right along the coast and compute errors. Now, satellite-based sea surface height data is really useful, but you can't get terribly close to the coast, and that means that it's not all that useful for trying to understand what actual at coastal water levels should be. Whereas the gauge data are really great for that. So that's why we only use the gauge data. But the downside of that is that the gauges, there's a fair amount of space between each one. Sometimes it can be 100 kilometers. Most of the time it's less. And so we have to just assimilate for the sorts of terms that we think we can reasonably capture given that limited amount of observational data. And so what we do is we low pass filter the errors to any signal that has a time signature of a day or longer, and create spatial fields from that. And in fact, we do a little more than that. We break it into two pieces, and I'll explain a little more in those details in a second, but you just think of this as correcting for things that are a day or longer for now. And then we run all the simulations again. So now with the assimilated fields put as inputs back into the model so we can get those sorts of dynamic interactions between the model and the corrections in there. And the result is, of course, our reanalysis. Now, getting back to that low pass stuff and the way it all works. So what we do is, the thing for you to look at for now is this light blue line, and then this purple-ish line. So the purple line is the correction term that we put in the second set of results. And what you can see is it doesn't exist below frequencies of about a day, but then it jumps up and it's correcting for things pretty well until at a magnitude that's not terribly different than some of the other, or than the water level signal itself. But then it starts to not be quite as needed for these very low frequency things. Whereas the error in the assimilated solution, this light blue line, immediately drops down. You know, this is log scale, so it basically goes to zero for any water level signals beyond a day or a couple of days. And that is because the assimilation works quite well, but it's also because we broke it into two pieces. Like I'd mentioned, the gauge coverage is kind of sparse, and this is really problematic because for something like sea level rise, where in 1979, there were no gauges across most of the Texas and Louisiana coast, like close to 1,000 kilometers of coast where there's just no obs. But we still want to capture at the very least seasonal water level fluctuations and for sure sea level rise, because otherwise we'd have this model that's sitting here and then once we get obs would drop down all of a sudden, which doesn't make a ton of physical sense. So we use some AI methods to actually come up with what sea levels at those locations for these very low frequency components would have been. And so we end up subdividing things into basically everything that's monthly and longer. We're able to correct for all the time using gauges where they do exist and AI methods to kind of come up with a surrogate for those actual observations when they don't. And then for things from 30 days to 1 day, you know, at that point, we don't think we can use AI to come up with what the errors were when there's just no data to go off of. So for that higher frequency stuff, we just correct when it's available. And this is, it's kind of a nuanced wrinkle, but it's really important from a lot of pragmatic standpoints. Because, for instance, if someone wants to use this data to get a sea level record, you know, sea level, the long-term sea level trends really need to look like what you would expect. Otherwise, it kind of loses a lot of its value and things like that. But on the bright side, it means that we get a set of data that gets a lot of improvements thanks to the assimilation, while still having a lot of pragmatic, just pragmatic and practical aspects of it representing what we know users are likely to want. Now, in terms of figuring out how we actually did, we've got two different sets of data. One is the training gauges, the ones that were used in the simulation. The other is ones that we held out for validation. It's about half and half, but when you look at the spatial distribution, this is very non-uniform, and the primary reason for that is again, like I said, just gauge coverage is not great everywhere, and these gauges, the ones that were used for the assimilation, are all open coast sites, so they've got decent coverage, but yeah, these ones don't, and that has some effect on the results, but we don't need to get into that level of detail today. So here's a look at RMSEs across all the data, the assimilated and unassimilated gauges, and then for both the baseline simulation where there wasn't any assimilation, and then the second one where there is. And the key takeaway is basically that errors, the RMSEs at least, go to about half of what they were in the baseline simulation. And that's also true. They go down by like 35 or 40% in the validation gauges, those ones where we're not actually training on, which is probably the most important thing since that's an indication of kind of broader model performance. The true picture is more nuanced than that because, like I was saying, all those gauges tend to be in these kind of up estuary areas and things like that. And no matter what, those tend to be the toughest places in the first place. So, you know, I don't know for sure what our true average performance is along all coasts. It's probably somewhere between these two. So maybe around 11 centimeters. But going back to earlier when I mentioned that really good surge models have errors of 30 centimeters, that's under extreme situations when you've got a really powerful storm in, so a vastly tougher situation. But still, at 11 centimeters of error, it's really, really good. It's excellent for most practical purposes. The performance is really nice. The other bulk error stats look pretty similar. The mean error is basically 0, and that's because that assimilation is capturing all that low frequency stuff so well that there's just no mean error to be left. And then to get away from these bulk stats and look at a couple locations, I picked two. One is Duck, North Carolina. That site was used in the training, the assimilation. It's a good representative open coast location, so I thought it made sense. And the other is Eagle Point, Texas, which was basically, I picked it because it was somewhere with more than 15 years of data that seemed to me like probably about the worst possible location without actually, looking at any of the results beforehand. I didn't want to bias myself when picking it. And that's because Texas has all these really deep, narrow dredge channels that this mesh has trouble getting right. It's nowhere near a site where there's assimilation going on. I mentioned earlier that for most of the entire time period here, there are no observations within several hundred kilometers of this location. So it's not benefiting from most of the gains in accuracy and things that other places are. But in spite of that, the error stats for it are actually really good. They're only a little worse than what we saw, or I'm sorry, a little bit better than what we saw in some of the bulk averages. And not terribly different from what we see at Duck. And in terms of the physical processes that we're capturing, so I'd mentioned that our modeling doesn't do sea level rise intrinsically. And so in the baseline simulation, red is the model, green is the error signal. There's this downward trend in the errors because the model is under-predicting more and more and more as true sea levels rise and rise. But that gets fixed really, really easily because sea level rise is kind of the lowest frequency, most gradual process that we might need to capture. And then when we look at things around the time of a storm, a lot of times there will be a bias in water levels around that time, either because seasonal water levels are high or because there's some precursor event or things like that. And we can see that here where, again, in green, the model water levels in the baseline simulation are kind of low. But once we assimilate things, that bias is taken care of. And then even around the time of the storm peak surge. By the way, this is Hurricane Isabel in 2003, which was the highest surge event for this gauge. We can see that in the modeled, there's this kind of growing under prediction of the surge response coming in that gets especially, over prediction in the surge response that gets especially big. And then even that gets corrected a bit. And again, this is probably mostly due to errors in the meteorological fields, but because they're on a little bit longer time scale, we do manage to capture them. So we get improvements across a really wide range of physical processes, but there are still pretty noticeable limits. And now we're going to look at the storm of record for Eagle Point, Texas, which is Ike. Ike, this is the other reason why I picked this location. I built the mesh that this was for, and even using the best bespoke, reanalyzed, magical wind fields in the world, this mesh has a really hard time with Ike because of the really tough, complex, and narrow bathymetry throughout Texas. And so in the baseline simulation, we badly underpredict. In the assimilated one, we do a whole lot better. It's 40 centimeters or so closer, but still kind of really badly. And this is just one of the limitations of this work is that, we're using intermediate resolution mesh. So the most extreme storms are not always great, but most other ones, any intermediate ones, anytime you're not right by landfall, the model performance is really good. And certainly for extratropical storms, it does a lot better because they're larger, broader storms, so Era 5 meteorology does a better job of representing them, all that jazz. So yeah, the bias is better, but the peak surges we do better, but they're still pretty junky, and it's just a known limitation of trying to capture these really extreme events. Here's some bulk error stats across everything. Again, we see the bias is removed, and the error variance gets shrunk down a fair bit. So overall, the model does a really good job. It does, all the results are better than us or NOAA had hoped for, which is really exciting. And it also just shows a lot of different cool things we can look at. For instance, this is the maximum water level across all 44 years at all the points. And well, what sticks out is that tides are kind of all the same in the open ocean, which we already knew. And then the storm of record becomes really apparent here. So we can see Ike, Katrina, Hugo, Sandy, some other ones if you zoom in some more. I think this was Dennis, if I remember correctly. Actually, I think it's Dennis here, and then actually it's an extratropical storm that happened in '93 down here. In terms of, so this is 10% exceedance water levels, in other words, the 10-year storm's peak surge. This is what we get in the baseline simulation. And then this is how those exceedance water levels change once we include the assimilation. And so not only do we get performance that is improved, but it's also pretty spatially variable. The effects of it depend, and so that's, again, one of the other really nice things about this is we can get better representations of both specific events, but also better representations of a lot of statistical quantities. And so just as a reference for that, here's a comparison. The x-axis is the observed 5-year and 10-year water levels, and the y-axis is what we get from the assimilated and unassimilated simulations. Blue, again, is the assimilated stuff, so the errors around the 5-year are really small and really good. They're a little bit larger around the 10-year. The variance increases some, but it's not bad. And when we look at histograms for that, we can see that they're low by a few centimeters on average for both, but not much. Certainly something that's really, really easy to bias correct for. And like I said, the variance grows a little, but it's still no more than 20 or I think the standard deviation on this was like 15 centimeters or so, which for extreme water levels is great. So it serves as a really good proxy record for coming up with what these things are along the thousands of kilometers of coast where we don't actually have this information. And we can do things with understanding the spatial error patterns and some other stuff that I'm gonna skip details on today. Now just a quick touch on, like I said, we wanted to make this stuff accessible and usable. So another group has been building for NOAA basically a data interface. I think it's gonna be through some Jupyter notebooks and other things like that, and hopefully a GUI that will allow people to select what areas and what time periods they might want things for, and even perform some basic calculations. Like an example I like to give is if you said, hey, what was the highest water level in New York City in the 80s? That's something that you can draw a box, you can set a time period, and then you can ask for the max value. And it's not that hard to spit out from this data. They're also doing gridded derived products on 500 and 2,500 meter grids, and including some GIS formats, because we know everyone loves to not have to work with an ASCII grid file. And then this is already starting to be incorporated into a whole lot of products for NOAA, including subseasonal water levels, sea level rise predictions, understanding high tides and nuisance flooding, historical storms, and yeah, starting to get into some things with extremes. I'm going to skip the future plans, but in short, this is something that's been one-time funded. But the hope is if there's enough interest and use that this will get picked up and we can continue to do the update the reanalysis each year, improve it over time, other wonderful things. Oh, and I forgot to mention something that definitely will happen and is happening right now is we're including the Pacific and also probably the Great Lakes in all of this. That work is ongoing. And then I've got a few more minutes, so I wanted to throw in a couple other random topics just for fun. So I've talked a lot about extreme flood hazards, and there are a lot of different methods to come up with these. And in some ways, we have a lot of confidence in these estimates, and in some other ways, we don't. I'm not going to explain what all these mean, but basically, this cluster of curves that all fit rather nicely together with each other is a host of different methods to estimate flood hazards. But in all the cases, what you're doing is you're using historical storms to try to come up with historical tropical cyclones, to come up with probability distributions of, hurricanes and doing things directly from that. This curve that looks wildly different is when you use, I don't know if people are familiar with the approach of CORA, where basically it's kind of similar, but you use historical tropical cyclone data to try to then come up with, basically produce a surrogate record of hundreds of thousands or millions of years of tropical cyclones by, it's a lot of bootstrapping and things like that, to resample distributions and then come up with a synthesized record of tropical cyclones in your area of interest. And that's how you come up with the probabilities. And so, they're both based on historical TC data, but different ones. One is local, one is more removed, and you get really wildly different results from this. And this is just one of the many ways in which getting a better understanding of what some of these true meteorological structures look like would be of huge value to the coastal flooding problem. And another one is, this is Hurricane Katrina. The red dots are the, I don't want to say QuickScat data, but I'm sure I'm saying that, and QuickScat wasn't even around then or something. It's one of the observational data sets of the actual flight level tangential wind speeds in Katrina. And the blue line that looks terrible is when you use a classic single exponential type fit, which is basically the same idea as a Holland model. And then the other one is when you do a double, you kind of sum two of them. And this reflects a lot of things. One, of course, the Holland model is not perfect, but a lot of times it does work well. But there are things like eye wall replacement structures that will actually kind of propagate out and affect the wind field out tangentially. And these sorts of things can have really sizable effects, especially in the far field. And like I showed near the start of this talk, where these far field winds can actually create some of the largest surges under certain circumstances. It's about the structure of the whole storm, and when you get some of these things wrong through too much parameterization, it can have really dangerous effects. And Hurricane Sandy was actually another case where there were some things like that, and it meant that you had places like the entire subways just going completely underwater. So yeah, it's just another case where there are a lot of these nuances that the devil's in the details, and for good reason. And I think I'll just leave it at that and say, any questions?
Do we have questions?
Thank you, Taylor. Very interesting. So my question is, if you wanted to get into the business of projection of water levels, future scenarios, maybe decadal or something like that, is that something we're close to being able to do? You think that these techniques could be adapted to do? The uncertainties are going to be large, so are those uncertainties so big that it's not practical?
A lot of it depends on, basically what processes you want to capture in that. If your goal is just to do sea level rise projection changes on how those affect what tides, flooding, what have you, that's not that bad. I mean, don't get me wrong, I have no idea what sea levels will actually be 40 years from now, but still, we've got decent senses of ranges of possibility, and it's we can mostly very accurately simulate, given the sea level is now this, what flooding might be. But yeah, then incorporating things like how storm climatology might change and things like that, and how those will propagate through. Those are, the uncertainties on those are pretty large, and those propagate quickly to uncertainties in water levels. And so those sorts of things, I think are where a lot of the limits in terms of predictability are right now. Yeah, there's this other piece about basically as sea levels rise, it really can change the landscape. Sediment accretion and erosion can change, and the presence of marsh structures and things like that. And so for places like southern Louisiana, where you've got tens of kilometers of protective marshes, if those start to heavily erode in the future, that will dramatically change the flood exposure there. But those sorts of locations are important exceptions to the rule, but still, exceptions.
Thank you for the presentation. So I just had a quick question with, obviously, modeling in the North Atlantic or that region has its own shortcomings and also some problems that may come up with the simulation and just kind of the project overall. And you did mention that you were, I believe, trying to branch out into the Great Lakes and also the Pacific. Is that correct? Mm-hmm. What kind of shortcomings or other problems do you think might arise during that, that process?
Yeah. It's certainly a case of everything's the same except for what isn't. On some of the lakes, particularly Erie and a huge swaths of Alaska, ice becomes a major factor, both shore-fast ice and just free floating, and that is as a messy complication that there's been a lot of research done, and I've seen several studies that have shown that models can do a whole bunch better. Once basically, you change some of the parameterizations and things like that to account for this. But it's still a bit of a question mark when we're trying to do things at climatological scales because, the problem changes, what you look at changes, all that. So that is a little bit of a question mark because I'm not aware of anyone who's dealt with that for this sort of thing. And then the other, there are various things, but the other really tough part is that on the Pacific, there's a lot of very large and long period swell waves that can come through, and through them by themselves and their wave setups, and also generations of infragravity waves and other things like that, they can really drive water levels at times, and that's something that we don't experience as much of on the Atlantic coast. And again, in terms of climatological simulations, I'm not aware of anything. I've not been able to find anything that's really even looked at model performances on those sorts of scales. And so it's certainly a bit of a gonna keep our fingers crossed, see what happens, and go from there scenario.
I have a question about the resolution of the data set, where there's this trade-off, I'd imagine, between having higher resolution, obviously, and more cost to it, and then the whole time period that you're simulating. So I'm wondering about, and maybe you said this, but I just missed it, why you chose 1979 to go back to in particular, and then also the possibility of doing a shorter time period, but maybe higher resolution and picking up some of those features, like you said, the deep channels, things like that might be missing.
Yeah, 79 was, actually, I think that might have been some of the reanalysis data that they started then, but it's tied into, some of the early satellite stuff coming on then, which helps with some of the meteorological model quality, and also the fact that the amount of coastal water level gauge data as you go earlier than then really starts to drop off. And so then, getting some of these things get more challenging. So that's why we chose that as kind of the starting point. Certainly, with shorter times, you can increase model resolution. Honestly, I suspect if this work does continue to get worked on, probably the first thing that will be done next is going to a higher res mesh, because they do exist and it can be done, but it didn't seem worth the sizable computational burden for this very first attempt. With a high resolution mesh, and the other thing that's being worked on right now is including better representations of the TC meteorology, basically using best track data and sticking that in. I think with the combination of those two, a lot of the remaining fundamental weaknesses or limitations, what have you, in this stuff will be pretty well captured. Not to say there won't be plenty of other work, but I think those will probably help really deal with a lot of the most glaring ones. There is a lot of potential, though, to your question, for higher res and more refined and more physics-informed modeling. We are hoping that this stuff does get used for doing some more localized and detailed modeling. Like, we assume that the solid earth, for instance, doesn't move, even though coastal erosion is a core component of seasonal cycles in sediment transport, of course, in storms, in barrier overtopping and things like that. There's a lot of dynamism that can be done there, but the modeling requirements for that are 1 or 2 orders of magnitude higher than what they are for the stuff we do right now. So it's that sort of thing as well outside of what could be done in the sort of reanalysis state right now.
Okay, great, thanks. Oh, we do have a Slido question. Okay, from Rich Rotuno. I've been going to beach in North Carolina for almost 30 years. I've noticed in recent years the streets flood easily. Is this phenomenon something you can comment on? Is it affecting beachfront real estate values? Okay, there you go.
I hesitate to comment on the real estate values. That's, yeah. Though I will say, back when I was doing FEMA coastal flood hazard studies at my old job, it seemed really weird. I was like, I know how these things that are very influential on property costs are going to change before they get published to the public. Oh God, I feel like I can't talk about this at parties. Like, it was weird. But anyway, to your question, yeah, increases in high tide, sunny day, nuisance flooding have been pervasive across a lot of the South Atlantic, especially Florida, for a little while now. And I don't know your specific location, but my guess is it's probably sea level rise that's driving the increase in those sorts of flooding events. I do know that in some parts of Florida, yeah, those nuisance things are becoming pretty serious nuisances. But again, I don't know about the property values.
Great, thank you. And with that, let's thank the speaker once more.